All right, so in this lesson, calculus, actually this is definitely AP Calculus 30 material. So this is one of our first videos, so one of the first subjects that we do in AP, Advanced Placement Calculus. We're going to continue on with integration methods. And so we just kind of got through U substitutions. You see here, we substitute in, for U, and then we integrate, then sub U back in. And that's definitely one method, but we're going to look at integration by parts today. And in lots of circumstances, you have something that you think, oh, U substitution is going to work, but it actually won't work. And we'll kind of get into a little bit some examples there. But integration by parts, I just want to sort of just say this about integration by parts. Let's just get to that. Okay, I'm going to type this out instead of writing it. Okay, so for every differentiation technique, there is a corresponding integration technique. And when we look at U substitution, that kind of came from the chain rule, right? We looked at the inner function and we said, how can we undo the chain rule? And that was that U substitution, which we just got finished looking at. Integration by parts is sort of the undoing of the product rule. Okay, and I'm going to show you how the formula for integration by parts actually comes from the product rule. Okay, and I'll probably write and refer to integration by parts as IBP, integration by parts. Okay, so this is sort of how it goes. Now, obviously, you have to take into some consideration the chain rule when you're doing integration by parts as well. But I'm going to show you how the product rule leads to this integration rule. Okay, so let's say that we have some function that looks like this. It's a product of two functions. Okay, and if we go back to our other techniques, okay, so look at this. Look at this. We have e to the power of t cubed times t squared. There's two differentiable functions, right? Again, here's just one function, and is that a 2 there? I think that might be a 2 there. So there we go. We can differentiate 2, right? The derivative of 2 is 0, but two functions that are differentiable. And so if we take a look at two functions that are differentiable, and we actually take the derivative of this function. So let's take the derivative of f of x, g of x. Well, what's that going to be? It's two functions that are multiplied, so we enact the product rule, right? Derivative of the first times the second plus the first times the derivative of the second. Okay, so that's what we have. That's the derivative there. So that's okay. Now let's just say that we want to integrate, and let's integrate this whole situation here. So if I take the integral, right, of everything you see here, well, integration is the opposite of differentiation. So I end up with f of x, g of x back, right? Taking the integral is undoing the derivative. And over here what I would have is I would have the integral of f prime of x, g of x, dx, plus the integral of f of x, sorry, this should be, I missed the g prime there, g prime of x, g of x. Okay, so derivative of the first times the second plus the first times the derivative of the second. Okay? And what we can do with this is we can actually rearrange this. So what I'm going to do is I'm going to bring this over to the left side, and you'll have to rewrite this. You don't have the fancy technology, but I'm going to rewrite this over to the left side. This is now our integral, and it's going to equal, because I'm going to change this over to the other side as well. So both of those are still going to be positive. This one I'm going to move over here because it's going to become negative. So I'm sorry if this was a little bit confusing, but I'm just rearranging my original equation. Okay, so let's go back and see that. Okay, so I'm pulling this over, and here we go. I'm just going to rewrite this. No, it won't let me. Okay, so we get this expression. Now, this actually is the formula for integration by parts. And you may be thinking, okay, what? We took the derivative of something and then we just integrated it back and we rearranged some terms and now we have a new formula? Well, yeah, we do. Look at, this is an integral sign, right? So if I want to find the integral of two differentiable functions, and yes, this is a derivative, but I'll explain that in a second. If I want to find the integral of this product right here, this is other terms how you can explain it. And this is the formula for integration by parts. Now, I understand what you may be thinking. You may be thinking, that looks a lot more complicated than when we started. But the hope is, and the plan for this, is that this integral over here, okay, is going to be a little bit simpler. Hopefully, if we do things right, this is going to be a simpler integral to integrate. This expression right here. That's what we're going for. And if you think about the term of what this is called, integration by parts, think of it this way. If this is the format for our original integral, and I write this integral like this and like this, I am splitting it up, I am more or less decomposing into simpler parts. Okay? And what happens with simpler type questions is this is all you have to do, and this becomes really easy to integrate. Sometimes it collapses into one term. Sometimes it just can be done mentally. In the tougher circumstances, then you can kind of start over and see this is another integral, and you can write this in terms of, like for example, you can go, f of x 2 times g of x, 2. You can basically do integration by parts twice. Okay, writing it in terms of a hopefully yet simpler integral, and so on, ... And if that still doesn't work, if this one is still not easily integrated, you can do it again a third time, and so on. So we basically, integration by parts, okay, is a way of decomposing a larger, more complicated integral into something that's really simple, okay, or at least easier to figure out. Now I'm going to do some examples, and we're going to work with this. But the bottom line is this is your integration by parts formula, and the hope is that as we split up this big integral, like this right here, that we will have, obviously, this is pretty easy right here. You notice that we have to integrate. This is a derivative right here, so I have to get the original function back. So I have to integrate this part. And over here is the derivative, so I have to differentiate this first part. But I can basically rewrite those things in a bit of a simpler term. Okay? Questions? Okay, so what we're going to do is we're going to use this. We're going to do a question from our textbook, and we're going to use this, and I'm going to show you how this works. And then, just a heads up, I am going to show you a shortcut method, which I really like, called the DI method. I'm going to show you that either later in this video or in another one. But I'm going to show you how to do that, and it's going to make this super, super straightforward. But it is important that you see that this works, okay? So let's do a simple example from your text. All right, so here's our first example here, the indefinite integral of x times e to the x dx. Now, if you're looking at this, you might think, well, why don't we try use substitution? And you can try use substitution. The problem is that if you choose x to be u, then du is 1 dx. And if we're going to try and substitute things back in, you're going to notice that you have this whole function that you can't eliminate. You can't deal with it. So use substitution is not going to work here. Use substitution, if you recall, it kind of works when all you have to do is multiply by like a fraction or something, right? To get, to insert this. If that's all you need, then use substitution can work. But in this case, use substitution is not going to work. And in this lesson, I'm not going to go any further than that, other than to tell you that you can go ahead and try it. but you're going to run into issues. If you run into issues with u substitution, then integration by parts is what you're going to have to take a look at. Now, okay, so what we want to do here is identify what's going to be kind of the first function and what's going to be the second function. So we've got, let's do this, f of x, okay? We need to find f of x, and we also need to find g of x. We need to identify g prime of x and f prime of x, okay? Because you see, we need all four of these to be identified and to be placed properly in here, right? So this is our given integral, which is going to fit into this spot right here. So if this equals this, what does x equal here? X equals f of x. Now I'm going to talk to you later about how to choose which function should be f of x and which one you should choose to be the derivative of another function. But for now, let's just take the first one. These ones are going to be pretty easy, okay? So f of x is x. What is e of x then? E of x is going to be g prime of x, exactly, okay? So e of x is going to be g prime of x. Okay, does everyone see that? Okay, so that's the first one, and this is the second one. It's not g of x, because in this formula, this is the derivative of g of x. So now what you see is we have to find basically the integral, or the antiderivative of e to the x. And here we have to find the derivative of x. So the derivative of x is 1 dx, right? And we should say over here too, the derivative, it always kind of follow that with a dx, okay guys? That'll come into play in more difficult questions, but let's put that there. And what's the antiderivative of e to the x? Yeah, e to the x. The one nice thing about e to the x that we really like is that it is its own derivative. That means it is its own antiderivative as well. So we have all four pieces now, and all we need to do, okay, is we need to substitute the appropriate parts here. So look at this. X goes here, and where's g of x? Oh yeah, right here. That goes in there. Everybody see that? So this integral, which is this right here, equals x times e to the x. That's the first step. Got that? Let me just get rid of some of this stuff here. Alright, so that's the first step. The second step is identifying this second integral here. So there is another integral, unfortunately. That's no big deal. What do I put in this integral? What's f prime of x? I go back to my list here. Well, that's just 1 dx, okay? So 1 dx. That's going to be part of my integral there. That's great. And that 1 really isn't even important, actually, but whatever. And g of x. Okay, where's g of x? Okay, that's e to the x again. So really, I hope you see that that 1 dx, I'm going to get rid of that 1. Look at what I've broken this down to. So this right here has now been rewritten. And this is rewritten in this form. This we don't have to do any calculus to at all. It's just two functions multiplied. And this, you see how this is now a simpler integration, right? And this will happen quite a bit, where you'll have something really simple you could just do mentally. And so we go ahead and simplify that, and we have x e to the x minus, what's the integral of e to the x? Well, it's just itself. And of course, because this is indefinite, we don't forget plus c, but we are done. Okay? That is it. That is the integral, or the antiderivative of x times e to the x. So it gets a little bit complicated, right? It's not just a boom, boom, you're done. This formula really helps. And like I say, I am going to show you, now that I've showed you this, I am going to show you an alternate method, and I'll do both methods here for a little bit. But I'm going to focus on that shortcut method because it's super awesome. And even for tricky ones, it's going to save you half a page work. Okay? But do you have any questions about that formula and what we did here and how to use that formula? You mean over here on this side? Well, I mean, if I was being real here, okay. So this, like this right here, equals this. So really what would go here is the original question. See, that's the answer, you see. The integral of x e to the x, yeah. So if I was being complete there, I didn't even leave that blank. But this integral here, remember, we're looking for an expression that represents the antiderivative of this inside stuff. And that's what it is right here. Okay? All right, so the next thing I'm going to show you is this shortcut method, okay? And this is called the DI method. The DI method. Now, I know you haven't had a lot of time to work with the original, the formula for integration by parts right up here. But this method, I think, is going to be super helpful. And I'm going to do the exact same question, but I'm just going to show you a little different way of doing it. And actually, we're going to bypass the formula totally. And the reason why I like this method of integrating by parts is because, do you remember when where was it? Oh, I think I erased it already. But in my notes previous, remember I said that you may have to do integration by parts again and get a whole another expression. And then if this integral still isn't very easy to solve, just mentally, right? You may have to do integration by parts again, and it can get really long and ugly. I just be honest with you, and you know about that, right? When we did this differentiation, and it went on and on and on. But this method is really, really neat. So this is how it's going to go. We're going to do the same question. All right, so if we do the exact same question here, what I want you to do is just over to the side, I want you to put just a little table. So deriv and integral. So there's a derivative sort of column and an integral column. Okay? And what you're going to want to do is we're going to want to choose which of the two functions, okay, because we're going to be dealing with just two functions in these ones. Which one are you going to want to take the derivative of, and which one are you going to want to integrate? And so in later on, I'll help you decide when you don't really know what to do. I'll help you to figure out what to decide. But if you have an algebraic, just monomial like this, like x or 2x squared, or that's the one you're going to want to differentiate. Okay. So in this case, we're going to take x here as being the function, f of x that we want to differentiate, and then e to the x, we're going to want to integrate. So this is going to be easy to differentiate, and this one, of course, because it's e to the x, is going to be easy to integrate. So that's what you want. You say, which one's going to be really easy to integrate? That's going to be almost your deciding factor. But anyways, the other thing you need to do is you need to write plus sign here in the first row, and then minus, then plus, alternating, okay? Minus. So just maybe do like 4 rows of plus, minus, plus, minus. Okay. Now, this is basically, we're setting up this DI table, okay? If you remember in the previous lesson, or the previous question here, what did we do? We had function, its derivative. We had function, its derivative. Or if you look at it another way, we had a derivative and its integral. A derivative and its integral. So really, it's derivatives, integrals, that's what we're doing. We took the derivative of x, and we took the integral of e to the x. So we're basically going to put that in this chart. I'm going to take the derivative of x. I'm going to take the integral of e to the x. Okay? So what we do is we work down now, and we say, okay, what's the derivative of x? It's 1, right? Now, we don't stop there. This is the cool part of this. We don't stop there. We're going to go we're going to differentiate again, okay? And I'll tell you why in a second why we're going to do that, but what's the derivative of 1? 0, okay? So here's the first key right here. If you, in your derivative column, you differentiate, and if you get to 0, you stop, all right? That's a good thing. And what that means is that's going to be your last row on this little chart. So then you go over to the other side. Okay, and you're going to love this. You are absolutely going to love this. It's the best thing ever. You go to the other side and you say, what's the integral of e to the x? Well, that's pretty easy. We know that. It's e to the x. And because we need 3 rows, you do it again. And it's itself. Oh, wow. Okay? So you have a little derivative and integral chart. Now what you do is you have to take into consideration the sign here, but you want to start here at the function that you differentiated, and you want to draw a diagonal line to the next row here. So diagonal lines, this one to this one. Then go down to this one. And of course, we're taking into consideration the sign in a minute. and another diagonal row. What we're going to be doing is we're going to be multiplying. Okay? We're going to be multiplying here and multiplying. These arrows are multiplication. The reason why 0 is good is because it doesn't matter what's down here now. When you have 0 times this, it's going to be 0, right? So you're going to end up adding 0. That's when you know you're going to be done your expression. So that's why 0 is great. So watch this. We go straight from this table to the answer, okay? And watch this. Positive x times e to the x is x e to the x. The next row, negative 1 times e to the x. That becomes a minus 1 times e to the x is just e to the x. And because we have a 0 next, that means we are done. We add c. Dun, da, da. You're done. Isn't that exciting? So there we go, yeah. It's exciting, okay? It's very awesome. So we bypassed the whole formula thing, I guess, in a sense. And we just kind of use this handy-dandy little chart. So that's the DI method. You're going to love it. Let's go through another example, and I'll show you some more examples of using that DI method. Okay, so if we look at this integral right here, I want to focus on one thing actually, because here's one function, here's the other function. Now, inside the cos, it's one thing to be able to find the integral of cos, or the antiderivative of cos, but then you have this 3x in here, right? So if you wanted to end up with a cos of 3x alone, what is it that you would want to differentiate to make this happen, right? So we have to go backwards and find out what this function is. Now, I'm not really sure how many of you would be able to do this very quickly because of this 3x here. So we have to kind of remember what we're doing. So what's the antiderivative of cos? Antiderivative of cos is, okay, well think of it this way. Yeah, it's going to be sine. Positive sine or negative sine? That's the tricky part, right? So I don't know what you remember, if you remember what the derivative of sine is. I remember this, my first memory. Okay, I think, okay, sine, positive sine gives positive cos, okay, as a derivative. So if we have cos, and we take the antiderivative of cos, that's going to give us what? Negative. It's going to give us negative sine. Trying to find my. Okay, I'll tell you what. Let's go to the chart here in our textbook. So we get this table of integrals here, and the integral of cos is positive sine, okay? So we've got positive sine is our integral, and of course, whatever you have in here is going to stay in there. So that's going to be 3x. You're going to always retain that. But what's going to happen is when you take the derivative of something, right, you would apply the chain rule. So you actually would multiply this whole thing by 3 at the end, right? So I don't want 3 cos x, okay? Instead, I want just plain old 1 cos x. So that's when you go 1/3 here to counteract what would be the chain rule when you take the derivative. So the integral of just cos of 3x dx is going to be cos goes to sine. You leave the input in there. And then because you don't want a 3 at the end of it, right? There's no 3 at the end of it. You have to put this 1/3 here. So you have to counteract what would be the chain rule in differentiation. Okay? So that's that. We'll get more practice with that. But anyway, so this is going to be 1/3 cos x here is going to be 1/3 sine of 3x is going to be the integral here. All right. So let's take a look at what we're going to do for. Now I'm a little bit crowded here now. So okay, let's just go here. D derivative, right? And I for integral. All right. So what did we say about monomials, algebraic kind of monomial terms? Those are the ones that we're going to want to put in what column? What column are we going to put those in? Yeah, derivative. We're going to put those in the derivative column. Okay. The cos of 3x, although it's not a slam dunk, it's not too terribly hard. So we're going to put x there, and we're going to put cos of 3x here. And of course, we're going to want to put plus, minus, and so on. All right, so now let's differentiate. And with this one, again, it's just the same sort of thing we did last question. The derivative of x is 1. The derivative of 1 is 0. So that's good. We have a good sign here. This is not going to happen all the time, but for these simple examples where you do have this monomial here, it's going to get to 0, right? So the integral of cos of 3x. Well, we did it over here. So cos goes to sine. You leave the input variable. And because I don't want a 3 over here at the end, I have to put 1/3 here. Okay? So that's the only tricky part here, is taking the derivative of or the antiderivative of this. But now we got to do it a third time. Okay? We got to make a third row here. So what's the derivative of the antiderivative of sine? Okay, well, if you go back to your chart here, the antiderivative of sine is negative cos. Okay, so the derivative of sine is cos. The derivative of cos is negative sine. So if you want a positive sign, it's got to be a negative to begin with. So this is going to be negative cos, going to be 3x. And again, we have to take into account the chain rule that would be to differentiate here. So this is 1/3, but we also have to multiply by another 1/3 in this step. So that becomes 1/9. All right. So with this method, even though it's pretty slick, the only problem is that sometimes you're going to have to take the integral twice. But remember what I said with this formula up here, you still may have to take the integral twice or 3 times as in this formula. So it's not like you're doing anything extra. It's just this chart sort of bypasses filling out that formula and writing things over and over again. All right, so we got to the 0 point here, so that's where we said that's the last row. And of course, what we do now is we make our diagonals and we do this multiplication. Okay, keeping in mind the signs here. So the integral of x cos 3x, right, is going to be equal to, okay, 1/3 sine 3x times x. So let's say that's 1/3. I'll put the x next, then sine of 3x. Okay, where these brackets are not really matter. So that's that product. And then this is going to be a negative, but is this a positive or a negative here? It looks a little funny, it's not a minus. That should be a negative, right? So that's going to be a negative times a negative is plus 1 times this. So plus 1/9 cos 3x. And because that's the last step there, we just add the c, and then we're done. So this is your answer right here. Right here. And really, we did integrate more than once. We actually integrated twice here. And so with the chart, you know, we didn't have to rewrite all the steps, and you didn't have to take half a page to do it. So this is that's the DI method for that. So there's another example, and like I say, we'll do lots more examples, but I think we'll stop the lesson there for now, and just maybe do more examples. But that's your lesson for integration by parts. What we've done is we've taken a look at the formula, how to rearrange the, how to come up with that integration by parts formula. We've used the formula to solve some, simple integration, and then we learned the DI method. Okay? Do you guys have any questions?